assignment number 15, it was this question about, it's another sequence question just like the assignment before it. So let's get straight into it. Now this notation again looks a bit weird, so probably what I suggest is you just play with it first. So let's just choose k to be a constant that we want. Like let's choose, I don't know, 54. We've got the first term is 2, and then we've got this kind of what's called a recurrence relation. Now you've probably seen something similar at GCSE, but let's just lay it out really, really heavily. So un plus 1 is, I've made k 54, so I'm just going to put that into there. And now I'm going to say if n is 1, then I have u1 plus 1, which is 2, equals 54 minus 36 over u1. But I know what u1 is, it's 2, so I put that in. 36 divided by 2 is 18, and I get 36. And that's u2. So now if I use n as 2, I get u3, because 2 plus 1 is 3, and then I have the un becomes a u2. But I know u2, that's 36. This becomes 36 over 36, which is 53. And likewise, I can keep going. u4 would be this over u3, which gives me some decimal. Right, so that's just how this works. Now the question they're asking me is determine the values for k. So I'm not allowed to just choose my k. It's saying find the values of k for which the sequence is constant. Now here's the recurrence they've given me. There's the starting thing. Now a constant sequence is just a sequence that stays the same all the time. Like it never goes anywhere. So here's my sequence, un plus 1, un plus 2, and so on. Now what this is saying is I need un to be equal to un plus 1, which is equal to un plus 2, and so on. Right? But this is cool because I know what u1 is. It's 2, which means u2 is 2, and u3 is 2, and un is 2, and so is un plus 1, and they're all 2. Right? If I start at 2, it's a constant sequence, and they're all 2. So this term is 2, and this term is 2. And this looks like something I can do. 36 divided by 2 is 18. Add 18 to both sides, and I get k as 20. And if you want to, you can check this, right? If you wanted to, you could use k as 20 in the original sequence. You could start with your original value of 2, and you could see, well, 36 divided by 2 is 18, which gives me that u2 is also 2, and therefore I'm good. And you could even go further if you really wanted to, but yeah, k is 20. Okay, what about the next bit, part B? Periodic with period 2. So what does this mean? Well, for a sequence to be periodic with period 2, what it means is it repeats itself every 2 terms, right? So it goes like this, 1, 3, 1, 3, 1, 3, or like this. So it repeats itself every 2 terms. Now, what does this mean for my UNs? Well, it means UN must be equal to UN plus 2. Okay? Which means, for instance, if n was 1, that means u1 is equal to u3. But I know what u1 is. It's 2. Because it said in the question that I was starting at 2. So that means I need u3 to be 2. Right, so let's go back into here. I know what u2 is. That's k minus 36 over u1. But I know u1 is 2. So let's put that in. And I get u2 is k minus 18, which is what I found last time. Now let's find u3. u3 is k over 36 divided by u2. But I know 2 things here. Firstly, I know u3 is equal to u1, which is equal to 2. So I can replace that with a 2, and I know u2 is this thing. So I can replace those both in, and this looks promising. This looks like something I can probably solve. If I, for instance, make this k into k minus 18 over k minus 18, I've just times this one essentially by this top and bottom. Then I've kept that the same. Now I've got a common denominator, so I can expand that out and put the minus 36 in with it and just keep the denominator. Now I can times both sides by k minus 18 to get myself 2k minus 36 is equal to this numerator here. Rearrange and solve. I can factorize out, which gives me k is 0 or k is minus 20, which means k is 20. Sorry, k is 20. Now, let's look at these 2 results here, because looking back at the top of the page, I already have k is 20 gives me a constant sequence. So how have I also got that k is 20 gives me a sequence that's periodic with period 2? Well, that's because this constant sequence very technically has period 2, right? In the sense that every second term, it repeats itself. The condition I gave on my u's was that this was equal to this one. And this, you know, that's good for this, right? That works. Even though I didn't really want it to, I wanted things that changed in the middle, but it does work for it, which means this thing is an answer, but it's not really correct because it gives me a constant one. And it just so happens that if you have a period of 2, constant sequences are a subset of things that have period 2, right? They're just the ones where the things in the middle are also the same. Now I could check is with k equals 0 here. If I put k as 0 into here, do I get, and u1 is 2, do I get a sequence that has period 2? And pause the video and test it, but you do end up with this here. So k is 0 is correct, and I can put that up there. Okay, periodic with period 4 now. Okay, so here are my conditions. U1 is 2, and this is the recurrence relation. Periodic with period 4 is something like this. Every 4 terms, it repeats itself. So on the 5th term, you could say it repeats itself. So every 1, 2, 3, 4 terms, it starts repeating itself again. So all of these repeat themselves after 4 terms. So what does this mean for my sequence? Well, I need this term, un, to equal the term that comes after 4 more. So 1, 2, 3, 4. Right, so I need un to equal un plus 4. So if n was 1, I need u5 to equal it. But I know u1 is 2, so I know I'm going to need u5 to be 2. I essentially need the 5th term, as you can see from here. I need the 5th term to equal the first one. Yeah, that's the 5th term there equaling the first one. Okay, so I need the 5th term to equal the first one. So let's get into this here. But maybe before we do, let's notice that just like before, this will let in sequences that are periodic for a lower period. So like constant a sequence. This rule lets in a constant sequence, right? Because the 5th term is the same as the first one. And likewise this one, the 5th term is the same as the first one. And also the 2nd term is the same as the first one. So this condition here, which I'm using to ascertain whether or not I've got a period 4, is going to let in sequences that have constant periods, or period 1, I guess, and period 2s as well. So we'll need to check our answers just like before. But anyway, let's get into it. So u2 is equal to k minus 36 over u1. Now I know what u1 is, that's 2. And we've already worked this out. 36 over 2 is 18, so I get k as that. u3 is k minus 36 over u2. But I know what u2 is, that's the red thing here, so I put that in. And now I've actually already sorted this out. I sorted it out on the previous page by multiplying this by k minus 18 over k minus 18. And eventually I got this when I sorted it out. So I know that u3 is this, and just pause the video, go back to see me do this again. But this here I've already done, and it's this. Okay, so that's u3. Now u4 is k minus 36 over u3. So I need to say u4 is k minus 36 over this whole green thing, which is there. Now we saw this in the previous couple of assignments when we have a whole number divided by a fraction. And there's a cheap trick you can do here, which is well worth bearing in mind to save yourself lots of time. But when you have a constant divided by a fraction, you can take the denominator of that fraction and just jump it over to the top. Right? So it becomes this. And it's probably the quickest way of dealing with this whenever you see it. You just jump that over to there. Okay, now I expand that out. I can also change this k to be, well, I can multiply it by this over itself. And then obviously these k's just increase by 1 power. And I end up with this. And now I've got a common denominator. I've also expanded this out. Just be careful here. Well, 36 times 18 is quite annoying, but in any case, you can do it. Just be careful here because you're taking away. So on this numerator here, you're going to get k cubed minus 18k squared. Those are on their own. Minus 36k minus 36k is minus 72k. And then we've got a minus 648, which is 648. And that's my u4. Colored it blue because, of course, I need to go to u5. And remember, u5 is the last thing I'm going to have to do. Right, so u5 is k minus 36 over u4, which is k minus 36 over all of this. Now I know two things here. Firstly, I know that trick that I did on the previous slide. I know whole number divided by fraction. I actually did it right here. Whole number divided by fraction. I can move that bottom part of the fraction over to the top. The second thing I know is that u5 must be 2. So I'm finally kind of arrived at something that I kind of want, which is 2 equals a bunch of k's. And I've moved that thing there over to the top, just there. Right, so that's what I end up with. And now here it is. I've just got something in k, which means this might be solvable. I can expand out this top bit, and I can also change this again to, just like I've done a couple of times before, to have a denominator of this here. So I'm going to times this by this over itself to give me this. Done that same kind of idea a couple of times before. I am going to expand this out. Now, 36 times 18 I've already done. That was the 648 that I did in the last slide. 36 times 36 is annoying, but it's actually the same as 36 times 18 doubled, right? Because 36 is double 18. So I can just double this to get that. So it's not that bad. And that is the worst number that I'm going to have to do in this video. Now I have a common denominator, which means I can just add the numerators. Now be careful again with this negative sign. Be really careful. You don't want to make mistakes there. You've got k to the 4. This is the only cube, so that's fine. Minus 72k squared minus 36k squared is that. 648k minus 648k. Well, that's just 2 lots of 648, which I've already ascertained as that, so I can just put that in there. And then I've got a minus 1296, which is that, over that same denominator there. Now this is looking good. I can just multiply that over there to give me this. And now I notice when I expand this, so I'm going to expand it, but I notice 2 times 648 is going to cancel with the 1296 over here. So I'm actually going to get rid of all the constant terms, which is great. And I end up with this. Just pause the video if you need to catch up with some algebra and just make sure that you understand what I've done here. Okay, so this is what I end up with. Now, again, when you solve any kind of polynomial, you always want to make one side 0. So take away 2k cubed, add 36k squared, take away add 144k, and we get this. Now this is a quartic, but it's a quartic that has no constant term. It's got k's everywhere, which means I can take out a k, and I can say the solutions to this are either k is 0, or this thing in that bracket is 0. Now ignore the red just for a second. Okay, a couple of things to discuss here. Firstly, solving cubics is not fun. However, you need to think, do you have any information here that's going to make solving this cubic easier? And the answer comes maybe from this k is 0. Because remember, k is 0 gave us the things that have period 2. But I already talked about how things with period 2 are just a subset of things with period 4. And then you realize, likewise, things with period 1, otherwise known as constant sequences, are a subset of sequences with period 4 as well. So if whatever k gives you constant sequences also gives you sequences with period 4. So k of 20 gave me constant sequences, so k of 20 must be a solution to this as well. Because if it gives me constant sequences, it gives me period 4 sequences, because these are technically period 4. So k is 20 as a solution to this. And that's kind of like when you do normal A-level maths, you learn to solve cubics by finding one solution and then reducing it down. So if k is 20 as a solution, that means k minus 20 is a factor, which means I can factorize this out to k minus 20 times something else. Now, it's tempting. You could do some polynomial division here. I'm going to be much more lazy than that. I'm just going to notice to make a k cubed, I need a single k squared. And to make a 1440, I need a minus 72. And so now all I need to do is find whatever a is here that will give me this. And now if I expand this out really quickly, I get k cubed minus ak squared minus 72k minus 20k squared plus 28k plus this. And now, well, this must be the same as this. So if I just compare my k coefficients, I get minus 72k must equal minus 72k plus 28k. But of course, this cancels with this. Divide through and you get a is 0. So I know this term must be 0. If you feel more comfortable, just do polynomial division on that. If you feel more comfortable, but I just prefer comparing coefficients. So anyway, we were trying to solve this. We knew that k was 20 was a solution, so k minus 20 is a factor, and I now know that a is 0. So I can just reduce this quadratic to this, which is amazing, because I can solve k squared minus 72 is 0. Just move the 72 over, square root, and then notice that 72 is 36 times 2, which is 6 root 2. And I get my two answers for period 4, a plus or minus 6 root 2. You could test those if you would desperately wanted to, but I can't really be bothered. Okay, last part of the question then. In the case k is 37, show that un is greater or equal to 2 for all n. Now this is quite fiddly, but listen up carefully, because I'm going to try and explain this as carefully as I can. So u1 is 2 as always, and then this is the recurrence relation, but I've got k is 37 now. Now let's just figure out what u2 is. u2 is 37 minus 36 over 2, because u1 is 2. We've done this a couple of times. Now I'm not going to work out what this actually is. What I'm going to say though, is I'm pretty sure that's bigger than 2. You can work it out if you want to, but I think it's bigger than 2. Now what about u3? Now u3 is 37 minus 36 over u2. Now I know that u2 is bigger than 2, which means this fraction, this 36, is going to be divided by something bigger than 2, which is going to make it smaller than this fraction. Because this fraction is being divided by something bigger than 2, it's smaller than this fraction, which is only being divided by 2. So this whole thing here, when I take away a smaller number from 37, that's going to give me something bigger than I had the last time, right? So let me repeat that. U2 is bigger than 2, which means this fraction is smaller than this fraction. When I take away something smaller, I end up with something bigger in total. So I know U3 must be bigger than U2. But I know U2 is bigger than 2. So U2 is bigger than 2, U3 is bigger than U2, which means I can just repeat the argument forever. I can now say U4 is bigger, U5 is bigger, and so on and so on and so on. So I can just repeat that argument forever. Okay, next part of the question. So given in this case, so this case is when UN is always bigger than 2, which I just proved, or equal to, I guess, and the recurrence relation is where K is 37. So that's the case. Given in this case, the sequence converges to a limit. This thing here converges to a limit. Find the value of it. Now, what is a limit? Well, if you take a sequence that, maybe starts increasing, maybe at some point it starts increasing by, or it always increases by slightly less each time. And you eventually end up at a point where it's barely increasing at all, right? What you can say then is that for some really large value of n, so for some really far away term, un plus 1 is basically just the same as the term before it. That's what converging to a limit means. It means it increases by so little each time eventually, that eventually after a really large number of terms, you just end up with your next term just being the same as the term before it, right? And I can just call that value L for limit. So I'm going to say for some really far away term, this term is equal to the term before it, which I'm just going to label L for limit. And now we can go back into here and we can say, well, again, for some really far away terms, I just wanted these to be equal to each other and I wanted them to both be L. So I can just put those both in for L. And this is great because this definitely looks like something I can solve. This becomes 37L over L, which can just become that. Multiply both sides by L. Rearrange. And then this delightfully factorizes. Oh my gosh, that should be a plus, shouldn't it? Oh my gosh, I was so close to not making a mistake. That should be a plus. Massive apologies. Just imagine that's a plus. So here's your factorization. And so, of course, you've got the solutions. L is 36 or L is 1. But of course, in this case, all of my terms were above 2 or equal to 2. Which means that the limit, that number that all of my terms eventually get to, can't be 1 because they're all bigger than 2. So scrap that one, and we just end up with L is 36. And that's my limit for this answer. So that was a really lovely question, I thought. Really fun. Lots of good algebra in there that's worth practicing. And really well done if you stuck to it.